below the busiest bay in Asia. This is the Tokyo Bay Aqua Line, a road that goes under the ocean, surfaces on an island built in open water, then crosses the rest of the bay on a bridge. $11 billion, 9 years of construction, 23 years of planning before that. Without it, the trip from Kawasaki to Kisarazu was 100 kilometers around the bay, straight through central Tokyo. 90 minutes in good traffic, 2 hours in bad. Every truck, every day, choking the capital. The Aqua Line cut that to 15 minutes. But here is the question. Why didn't they just build a bridge across the whole thing? Tokyo Bay is only 15 kilometers wide at this point. A bridge is cheaper. A bridge is faster. A bridge is easier. The answer is sitting on the surface of the water right now. Tokyo Bay is one of the most crowded shipping lanes on Earth. Tankers feeding the largest port complex in Japan. Container ships coming in from Yokohama. A bridge across the western half of the bay would have needed pylons high enough for these ships to pass under, and supports rooted in a seabed that cannot hold them. Because under Tokyo Bay, there is no rock, just soft alluvial mud, 60 meters thick, the kind of ground that swallows a foundation and keeps swallowing. So they made a deal with the geometry. 10 kilometers under the water, 5 kilometers over it, and in the middle, they would build an island. In 1989, the first survey vessels start mapping the seabed in detail. What they find is worse than expected. The mud is not just soft, it is layered. Sand, clay, pockets of water trapped under pressure. A tunnel boring machine driving through this would feel the geology change every few meters. Sand wants to flood the machine. Clay wants to seize it. The pressure from above wants to crush both, and the depth keeps growing. At the deepest point, the tunnel runs 60 meters below sea level. The water column above it pushes down at 6 bars of pressure. That is 6 times the air you are breathing right now, pressing on every square centimeter of tunnel wall. If a single segment fails, the bay comes in. The engineers had a choice: use small tunnel boring machines and dig slowly, or build something the world had never seen. They chose the second option. 8 machines, each one 14.14 meters in diameter, each one weighing 3,200 tons. The cutter heads alone, bigger than a 4-story building. At the time of construction, these were the largest underwater shield TBMs ever built anywhere. Each machine is its own factory. The cutter head rotates against the mud. Behind it, hydraulic arms catch precast concrete segments arriving on rails and lock them into a ring against the tunnel wall. Slurry pumps push out the spoil. Pressurized seals hold back the water. The whole assembly digs, removes, and lines the tunnel in one continuous motion. But the real innovation is the slurry. Each TBM pushes a wall of pressurized clay-water mixture against the front of the cutter head. The pressure of the slurry exactly matches the pressure of the seawater pushing back through the mud. Too low, and the bay floods in. Too high, and the slurry blows up through the seabed and into the shipping lane above. The operators have to balance both in real time while the machine is moving. The advance rate they need, 500 meters per month, per machine. That is roughly 1 tunnel ring placed every 90 minutes, day and night, for 3 years, without stopping. Stop the machine for too long, and the mud closes around the cutter head. The whole 3,200-ton unit becomes immovable, buried under Tokyo Bay forever. They launch the machines from both shores, 4 heading east from Kawasaki, 4 heading west from the planned meeting point in the middle of the bay. 200 meters above them, oil tankers continue passing every few minutes. The ships do not slow down. They cannot. The shipping lanes of Tokyo Bay are scheduled to the hour. To launch, they first have to dig a vertical pit on land deep enough to lower the entire 3,200-ton machine into position, 60 meters down. Then seal the rear of the pit, pressurize it, and and push the machine forward into the seabed using hydraulic rams that develop thousands of tons of thrust per ring. The first 10 meters of every drive are the most dangerous. If the seal at the rear fails before the cutter head is fully buried, the whole launch shaft floods. I am standing on the Kawasaki side now, where the launch shaft was sunk into the coast. From here, the operators could not see anything, just a screen showing pressure, a screen showing position, and a gyroscope that corrects every few seconds. 1 degree of drift over 10 kilometers becomes 100 meters of error. The two machines have to meet in soft mud, 60 meters down. That is the open question. How do you bring two 3,200-ton machines together, blind, deep, under pressure, and align them within centimeters? We will get there. First, the middle of the bay, the meeting point. There is no land there, so they had to build some. 2 artificial islands. The first, on the Kawasaki side, is 200 meters across. A circle of steel and rock dropped into 28 meters of water onto a seabed that does not want to support it. Before they could lay a single stone, they had to fix the ground itself. Sand compaction piles, thousands of them. A vibrating tube driven into the mud, filled with sand, pulled out, leaving a vertical column of compacted material that squeezes water out of the surrounding silt. They drove these piles of new ground, rising from a seafloor that had been mud since the last ice age. On top of this stabilized seabed, they build a 75-meter ventilation tower and a 90-meter inlet tower. Inside the towers, massive fans. Below them, the meeting point of the 8 TBMs. The second island is bigger, 500 meters long, 100 wide. This is Umi Hotaru, Sea Firefly, the transition point between tunnel and bridge. It looks like a cruise ship parked permanently in the middle of Tokyo Bay. 5 stories of steel and concrete, with a parking deck on top and shops underneath, anchored by sand piles driven into the silt floor. Both islands have to be ready before the tunnel arrives. If the islands are not stable, the tunnel cannot dock with them. If they shift even slightly, the meeting alignment fails. And then, the meeting itself. Halfway through the drive, the engineers face the moment that defines the entire project. 2 TBMs approaching each other from opposite directions, each one fully sealed. Each one holding back 6 bars of water pressure, each one weighing 3,200 tons. The mud between them is the only thing keeping the bay out. How do you connect 2 of these without flooding the tunnel? You freeze the ground. They drill probes ahead of each machine, pump in chilled brine at minus 30 degrees Celsius. The mud and water in the meeting zone freeze into a solid plug, a wall of ice strong enough to hold back the sea, while the engineers do something nobody had ever done at this scale. They mechanically dock the 2 cutter heads underwater. Hydraulic clamps engage. Seals press together. The space between the 2 machines is sealed off from the bay. Workers cut through the front of one TBM, through the ice plug, and into the front of the other. For the first time in human engineering, 2 pressurized shield machines meet face to face under 60 meters of seawater, without flooding, without delay. The error in alignment, after kilometers of blind drilling? A few centimeters. The crews on both sides shook hands inside the joined machines. Then they went straight back to work. The risk paid off. The mud held. The sea stayed out. But the project is not finished. It is barely halfway. Now they have to make the tunnel safe. Inside this twin-bore tube, one for each direction, 9.6 kilometers long, they have to put fans, lights, drainage, fire suppression, and an evacuation route. Because if a fire breaks out 5 kilometers under the bay, the people in those cars have nowhere to go. The solution: the tunnel cross-section is divided into 2 levels. The roadway sits on a deck halfway up the tube. Below the deck, a 4-meter exhaust corridor running the entire length. Above the deck, a fresh air supply. 2 4-meter exhaust fans rotate at the central island, pulling smoke and exhaust toward the wind tower at the surface. The tower itself is the elegant part, the Kaze no To, the Tower of Wind. Tokyo Bay almost never stops moving air. The tower captures the constant bay wind and uses it to push fresh air into the tunnel, backed up by mechanical fans only when traffic peaks. The system runs on the bay itself. Between the two bores, every 300 meters or so, they cut crossover passages. If a fire breaks out in one tube, drivers in the affected lane abandon their cars and walk through a sealed pressure door into the other tube. The clean tube becomes the escape route. The burning tube vents straight up the wind tower. The whole system is designed for one assumption: a fire will happen. Plan for it. And then the bridge. From Umihotaru, the road climbs back into the air and crosses the remaining 4.4 kilometers as a girder bridge to Kisarazu, lower than a suspension bridge. Lighter loads on the soft seabed below. Pylons spaced wide enough for smaller shipping to pass underneath, designed to flex during earthquakes, because this is Japan, and an unflexible bridge is a broken bridge. The bridge piers sit on board piles driven 50 meters into the seabed, anchored not in rock, there is no rock, but in deep layers of stiffer clay below the soft surface mud. Each pier is its own foundation problem. The engineers solved it 31 times in a row. The deck sections themselves were prefabricated onshore in 100-meter spans, floated out on barges, and lifted into place by floating cranes between weather windows. One section per crane, per favorable tide. The bay does not pause for construction. December 18, 1997. The Aqua Line opens. 23 years after the project was first approved, 9 years after construction began. The total cost? 1.44 trillion yen, roughly 11 billion US dollars at the time of opening. For the first months, almost nobody uses it. The toll was set at over 5,000 yen one way, the most expensive road per kilometer in Japan. Drivers stayed on the old route around the bay. The expressway designed to relieve Tokyo's traffic was almost empty. Engineering miracle, financial disaster. In 2009, the prefectural government cut the toll for ETC users to 800 yen. Traffic exploded. The road that almost no one wanted became one of the busiest expressways in the Tokyo region. The original plan worked, 15 years late, at a fraction of the toll, with the cost absorbed by public funds. In 2011, the Great Tohoku earthquake hit, magnitude 9.0. Tokyo Bay shook for minutes. Tankers swung at anchor. The seabed liquefied in places along the bay's edge. The Aqua Line held. Not a single tunnel segment failed. The flexible joints between the rings did exactly what they were designed to do: absorb the shear, redistribute the load, and stay watertight. The cement-mixed seabed under the islands stayed in place. The road was inspected. The road reopened. The traffic kept moving. This is the thing about the Aqua Line that gets missed. It is not a bridge across Tokyo Bay. A bridge would have been impossible. The bay was already full, already crowded with ships, already underlain by mud that could not hold a tower, already crossing one of the most active fault systems in the world. The Aqua Line is a road that admits the surface belongs to someone else. The shipping lanes belong to the cargo. The seabed belongs to the mud. The air belongs to the earthquakes. So the road went underneath all of it, then surfaced briefly on an island the engineers built themselves, then crossed the rest on a bridge low enough to flex with the ground. It is not a road that conquered the bay. It is a road that found a gap nobody else had seen. If a project this strange, a highway that disappears under the sea, surfaces on a man-made island, and reappears on a bridge, interests you, then there are dozens more like it